So thank you very much, first of all, for this nice invitation. So my name is Moens, or Marie-Francine Moens, and I'm going to tell you today about controlling your self-driving car with commands in language. This is work of two of my researchers, Thierry de Ruiter and Victor Milewski. We work together in the Machina project, which is together with also colleagues from computer vision, among which is also Tine Duitelaars and Matthew Blasco and Luc van Gogh. They are famous professors in computer vision. And in some of the papers that we show, they are also co-authors. So people are kind of afraid of, well, that's what the literature said, of being in a self-driving car. And we thought maybe humans would better trust a self-driving car if they could talk to that self-driving car. And in that respect, we made a survey with 254 participants. And the first question we asked was, would you trust driving around in a self-driving car? And you see that, yeah, the majority says yes, but still there is a substantial share of people who says no. Our second question was, if you would be able to give commands to a self-driving car, would you feel more confident driving around in such a car? And you see that more people say yes, then it's quite some increase. And then in a third question where we ask, well, I have to move you on top. Yes. Would you use a system that allows you to give commands to a self-driving car? Like, for instance, park in the shade? You see that many people, a majority, almost 83%, they are in favor that they could give commands in language to their self-driving car. So what if we can talk then to this self-driving car? So what would that entail? Well, first of all, well, here you see an example, pick up my wife, she's crossing the street. So that means that your system should find, well, first of all, should recognize the intent, picking up the action that the car has to perform. Then the car has to find the referred object in the scenery, because the human, the passenger, gives a command about a visual world which the car and the passenger share. So the wife who is crossing the street has to be recognized here in the street. And then next, you have to find a location where that action of picking up has to take place. And so you have to plan a path for the car to go to that location. And finally, yeah, then you have to execute that command. Now, in many real world situations, you might even want to go in a dialogue with your self-driving car. So you could say to your car, follow the tram. But yeah, here in this busy city, you see several trams. And you would like that the system asks the green one. And then you might say, no, I want the yellow one. And the system even then sees two yellow trams and asks the closest or the farthest, and then the passenger can answer the closest. So this is actually something that we want to realize. But there are, of course, a number of requirements. Your dialogue should be accurate, otherwise the trust in your system will decrease instead of increase. So your system should ask accurate, pertinent questions to the passenger. Also, the processing should be extremely fast. This has to happen all in real time. So any processing should be fast. And there is also the cognitive overload for the passenger. So we will look at that later, but that should be minimal, so that there also from the passenger side, there is no confusion. And of course, there are a number of challenges. We deal here with free language and eventually with free speech. In the examples that I will show and the work that we are doing is still on text, but eventually you want to have real speech, speech signals. the car drives in a natural visual environment. In the data set that we use, this is a city environment. And while driving, this environment dynamically changes. And also maybe the passenger might change his wishes or her wishes dynamically. So we started our research by building a data set, which we call Talk to Car. And it's part of the new scenes data set, which you might know. So these are images, well, actually videos with depth information, 3D information that are captured in the cities of Boston and Singapore. And we enriched these images from this video with comments, natural comments in natural language. So you see here a few, you can park up ahead behind a silver car next to the lamppost with the orange sign on it. So we used Amazon Turkers to create for us this data set, and we carefully checked afterwards also the data set to see whether these comments really make sense. Then in that first paper, we tested a number of visual grounding methods to see how good state-of-the-art methods perform for detecting the referred object in your command. And besides a few baseline methods which perform very poorly in terms of intersection over union metric, we implemented also one of the baselines was random selection of the objects that are recognized, also random noun matching. The nouns in the command are randomly matched with the objects. We used a number of more sophisticated models, and one is the MAC model, which is quite a well-known model used in visual question answering, where a representation of the text is made based on an LSTM neural network. And the representations allows that for the phrases in the text, the words in the text, you can create attention to certain regions or certain attention on the image actually. And your system, we adapted that systems that it can learn with bounding boxes, recognized objects in the image, and so we actually could learn the system to score the objects, the regions in the image for detecting the referred object. The stack model is a bit similar, but it uses neural modular networks. And then we also tested two simpler models, like this USM model, which is basically builds representations of the text and of the image, and through attention, it finds then the referred object. The SCRC model is similar, but it adds spatial information to the model. We also created 4 test sets, which have some difficulties, or most of them have some difficulties. So a test set, the test set depth, it looks at examples in the test set where the referred object is the farthest away. So because also the new scene data set, and on which our Talk to Car data set is based, it gives you depth information. So objects, referred objects, which are far in the image, they are of course more difficult to recognize or to detect in the image. The command length might play a role. Short commands are usually easier to interpret by the model, but long commands with lots of phrases and so on, they are more difficult. And then you have also images where there are ambiguous objects. For instance, where the command looks for a car, but there are many cars in the image, or looks for a person and there are many persons in the image. So depending on how many of these ambiguous objects are in the image, we also tested our models. And you see that these are all state-of-the-art models, and this MAC model clearly performs the best model, at least for these 3 last data sets, but also this CRC model with some spatial information did quite well. These were state-of-the-art visual grounding models that we used on our data set. Now, this MAC model, which performed best, it reasons by using the full image. It uses attention over the full image. And so we try to refine that model so that the model reasons when it builds representations of the language, that it reasons specifically with specific bounding boxes that are detected by a region proposal network in the image. And we wanted to see whether this improved our results. So here you see our proposed model. Now we have also feature maps of the respective bounding boxes. And then when the text is processed sequentially during training and also during inference, the system will learn to score particular words when for particular regions or bounding boxes in the image. And so it learns to score these bounding boxes, and when it is trained, you give a new command, and then the bounding box that obtains the highest score is then the referred object. And with this model, we could improve 10% this IOU metric, compared also to our best baseline. We have added here so an additional baseline that uses a technique of accumulated attention, which is also quite a common visual grounding technique. Of course, our model uses proposals, region proposals, so proposed bounding boxes, and usually there are many that are proposed in an image. And when there are too many, of course, it's difficult also for the system. Yeah, it's more difficult for the system to find a referred object. And we could make a selection by choosing the top K bounding boxes based on their probability of their detection. But when we choose then fewer bounding boxes, like top 8, there is the risk that, of course, our referred object is not anymore part of that set of bounding boxes. But with the top 16 bounding boxes, we could attain an intersection over union metric of about 60%. Now you see that our inference time, which for MAC was quite low, it increases substantially. We have a better model, but at the expense of an increased inference time, while the parameters of our model are still quite okay. We see the same. We see the same tendency of our model outperforming these baseline or these state-of-the-art models for our 4 difficult, well, except for this short comment, for at least for these 3 more difficult test data sets. So, as I said, we could improve by 10% this IOU, but at the expense of a larger inference time. To give more publicity to our data set, we organized, together with the colleagues of computer vision, we organized a workshop and a challenge at IJCAI 2020, so commands for autonomous vehicles. And this was, we had quite some submissions, and here you see, in this table, you see the top 5 best models, and you see that these models outperformed than our model by a bit more than 10% again. What is typical of these models? Well, they use transformer architectures, like the best model used a stacked visual BERT model, quite a heavy model with lots of parameters. And you see that for all these models that are the top performing models, that transformer architectures with multi-head attention, give you better representations, especially at the language side. They were better, creating better representations. But word attention still plays quite an important role in these models. But of course, yeah, this is not all. Finding the referred object, we also have to deal with ambiguity and underspecified commands of the user, like this one, follow the tram. There are so many trams here in this image. And not only we have to deal with this kind of ambiguity, it could also be that the system is uncertain about the recognitions and the scoring of these bounding boxes with the alignment in this reasoning with the language. So our next goal was how could we detect and report back this uncertainty of the self-driving car when a given command that when giving a command that refers to a specific object in the visual scene. So for all these models that you have seen before, they just use a softmax function to find the most probable referred objects in that visual scene. But that softmax might not always be reliable. So how can we capture that uncertainty? How can we better quantify that uncertainty of the predictions? And our second question was, how can we report back to the passenger this uncertainty? So the idea is, if you have a scene and a command, pick up that person. Suppose our system is uncertain about these two persons. Suppose it gives like 50% each of, well, in this simplified example, both are good candidates for being the referred object. So we want to detect jointly a reliable uncertainty and then ask feedback from the user about these detected objects. So, and there we foresaw two possible ways. So the user could touch a screen. You show these boxes on the screen together with the user command, and we assume the user knows his command and he can indicate the right person correctly. But additionally, also we generated a question in natural language that describes these objects, these individual objects. Because we felt also that gives also more confidence, that might give more confidence to the user that the system really understands what it sees. So we created, and we will see examples. Do you mean the person with a black dress or the person with a blue skirt? Now, our first problem is to quantify this uncertainty in a correct way. And in the literature, there are many methods for this purpose, but some of them are only useful for toy examples, and others are computationally very expensive, like the use of Bayesian networks, for instance. So we found that in our case, it worked best and was most efficient to use an ensemble of n visual grounding models. Of course, an ensemble is maybe also not completely the best solution, as you have now n models that have to run, but we thought they can be run in parallel on our self-driving car, of course at the expense of more energy that is being consumed. But anyway, this gave good results, and maybe future work on this uncertainty detection can even do better. So if we have n visual grounding models, then we use a simple heuristic. If they all vote for the same object, the same referred object, there is no uncertainty, and else there is uncertainty, and you know the objects that are causing the uncertainty. And so we saw that we went up to 5 ensemble models, so we could compute what we call certainty accuracy. So that is the accuracy when the ensemble all votes for the same object. So how often is that referred object then within within what is voted for? And you see that the certainty accuracy mounts up to more than 86% when we use 5 ensemble models. We can then also compute the theoretical intersection over the union. So you assume here that the passenger, once you present then the object that the system has determined to be uncertain about, you assume that the passenger will indicate the correct object. And then you can achieve an intersection over the union by selecting that particular object. And you see then we can, with an ensemble of 5, we can achieve an IOU of more than 78%. So here you see some examples for the command parallel park behind the car on the left. You see that the system adapts between these two cars. In this command, change lanes and get behind a white car, the system is confused by these two cars. Although this right one is a little bit yellow, the system is confused about these two objects. And here, after that signaling cone turn left, there are 3 cones on the road, and the system is confused about these 3 cones. Now, we also, there is also the problem that sometimes for certain cases, you have many uncertain objects, and you do not want to overload the passenger to select one of these or to generate questions about all these bounding boxes. So also in the paper, we describe different methods of selecting these K objects where we have to balance between maximally exploiting uncertainty and restraining the size of K on which that user interaction and question generation are based. But I refer to the paper because of lack of time for these methods. Again, when we look also, well, overall, we have this increase of 9% in intersection over the union by this uncertainty detection method and feedback of the user. And also we see the same tendency of improvement of our results in our 4 test sets. And then the second question, how can we report back the uncertainty of the self-driving car to the passenger? Well, we want, if we have 2 uncertain objects, for instance, for this command, pick my friend up in the yellow jacket, we want to generate a question that describes these objects. And here you see examples of questions that were generated by our system. So do you mean the first adult on the right or the first adult on the left? For this, we rely on attributes that we assign to these bounding boxes. So we separately trained attribute classifiers to better generate these questions for the user. Here you see another example for parallel park behind the car on the left. The system is confused about these 2 cars, which is logical because your query, your command is kind of underspecified. So the system has generated a question, do you mean first black car parked on the left or first car on the left? So to generate these questions, we just use a template, but the description comes from a text generation system that describes these bounding boxes. Here, for your information, you see some accuracy results of the attribute type recognition. So we defined classes, color classes, action classes. Person can be walking, can be crossing, and do other things. Also, location attributes were quite useful so that we can better define the location or describe locations with natural language in these visual scenes. And you see that these, yeah, that also inference speeds, we take into account all the time inference speed, and that there is quite some difference, and that, yeah, overall, I think neural network classifiers do well also in times of inference speed. And then with regards to the generation, the text generation process, we implemented many different models. So baseline models were classical image captioning models, but now applied to these bounding boxes of certain objects. We have then built models that used an encoder-decoder, CNN encoder of the image and the LSTM decoder of the textual phrase. Also that take into account a full image, but our best results were obtained with text generation models that take into account the attributes which were a priori generated. We can also include other information. We can combine this also with attention mechanisms. We can also include, like here in the CLS models, additional class information of these recognized objects. So we use also the labels for these recognized objects, which refers that we generate that we force attribute when we describe attributes of 2 or more bounding boxes, that they are unique, but that was not really so helpful. But what was helpful was that we use difference features but also between these visual features of the different bounding boxes, that we extra emphasized these features. And you see here different scores, typical scores, Météo, Rouge and Bleu, for text generation. Yeah, these were our results for this text generation task. You see also that models have different inference speed in milliseconds, and that our best models are not always the most cheapest in time. So this is always also a balance between these two prerequisites. Now, this is what we have done so far is not all. Currently, we are working on models that besides, so if you can park ahead behind the silver car next to that lamppost with the orange sign on it. You have detected the silver car, but you have still to locate the position. Well, the position. We locate that in this physical world. Basically, you have to locate that position where the action of park has to be performed, and this also for our other examples that we have. So that's actually what we are currently doing. So looking at the intent, looking at the location, 3D location in the 3D physical world. Also taking into account the ground plans of the street plans where the car is driving. And then we have to plan the path and to execute the command. Now, the question is, how can we do all this in the most efficient way, combined also with this referred object? So we want to more combine these tasks, possibly in multitask settings, and to see how can we do this in the most efficient way and still be very accurate. And then, of course, if you look at these videos of new scenes, because in the real world, when your car is driving, the world around you is moving. So you have to take into account that objects, people who cross the street, bikers or other cars, they move in different directions. So you have to predict this and take this into account. And it could also be that the passenger might change his mind and change his comments or slightly. So all these dynamics have to be taken into account. And as I said, now we work with written text. but if eventually you need speech and to actually translate in, well, to use not to transcribe speech, but start from the original speech signals and there perform the semantics, understand the semantics of the command in correspondence with the image, which also would speed up your process, because if you have to transcribe, this is an extra processing step, and also a step where you can make errors. So all these dynamics and the integration of speech is subject for our future research. So this brings me to the conclusion. I hope I convinced you that controlling your self-driving car with commands in language is really a challenging research topic. There are still many open questions to be resolved, and you have a number of constraints that you have to fulfill, like accurate dialogues, pertinent dialogues, latency has to go, everything has to be very fast, and you have to take into account the cognitive abilities also of your passenger. And also this technology, although it's very useful for self-driving cars, I think also it has many applications beyond autonomous driving, applications where humans interact with machines. So thank you for your attention, and I'm open for your questions.
Thanks for the great talk. It's really a challenging task in my understanding.
It's challenging, yes, absolutely.
It's super challenging. So I guess right now, probably we'll see if there are questions from audience. Otherwise, I do have a lot of questions myself as well. So if the audience has any question, you don't need to raise your hand. You can just unmute yourself. I guess you can do that yourself and then just ask. Or if you are too shy, you can just type, not using your language, but using text, using your text first. So yeah, so maybe I can begin to kick off. So first question I have, I've seen like a lot of like the slides you are talking about is about the visual grounding, right? So you have to recognize the object first. For example, using some 2D object detector to get the 2D boxes and compute IOU and etc. So that's kind of like a mature technique in 2D object detection domain or in computer vision. But right now, I think in the autonomous driving, either industry or academia, there are also tons of research in 3D object detection and tracking and prediction, right? So that's kind of standard way of recognizing object in 3D and then predict and then make planning. So how do you kind of integrate that into your like the proposed pipeline? Or for example, can we do 3D visual grounding and then using that to control your self-driving car and etc. Or
I think that's a right question. We also thought about that in the beginning, but we started with 2D because the state-of-the-art models were there to do our first experiments. And at some point we will have to move to 3D to execute a command and finding right locations and so on. But at this point, we only have done experiments with 2D, but I think it makes sense to ground language also to 3D. And the new scenes datasets offers you this information.
Yes.
So that's also handy to work with.
Got it. Yeah, that totally makes sense.
Yes, and our talk to car, it's our commands apply to certain scenes of the new scenes dataset, so they can still apply.
I see. But right now, the methods that you held in the last year workshop and challenge is using 2D.
Yes,
visual
in the
grounding,
workshop
right?
also. Yes.
I see.
Yes.
So probably like in ECC 2022, we'll see another challenge for 3D.
That's a good idea. Yes. Yes, that could be a good idea. Yeah.
Okay. Yeah. Thanks.
I will tell my colleagues. Yes.
Got it. Okay. I guess another question I have is that you talk a lot about how to resolve the ambiguity, right, through like back and forth question and answering between the machine, the autonomous driving car, and also the passenger, right? because there is always ambiguity. You don't know what the passenger is talking about. So first of all, the back and forth discussion really takes time, right? So for example, sometimes you will, let's say, take a few seconds to resolve a ambiguity. So it's really delayed in the decision making. So what about alternative options to do that, to resolve the ambiguity? For example, can we use a touch screen? Let's say on a camera or on something. So when the passenger say, okay, stop on the left or on the right behind a white car, and then there are two white cars, and then the car doesn't know which white car you are talking about, so you can just touch. I want this one, not that one.
Yes. That's also what we foresee. Yeah, that's our first option. You just touch the boxes that you mean. But we wanted also to see how well can the system generate also the description with it. We felt that maybe that could be an experiment in human-computer interaction, whether this is easier for the user when he also meantime he hears what he has to touch. But you are right, it should not be too long, because otherwise you lose these phrases should not take like 2 seconds or so. You waste your time.
Yeah, because you're like talking to a 2-year-old kid or something. So he or she doesn't understand what you're saying, I guess. Because I'm just saying maybe using touchscreen is a faster way to get this thing into product or thing in the industry, because I guess using the language and text probably it's still a research question, right? And probably take years.
I think so. Yes.
Yeah. Okay.
And also you could project text on the boxes or so. I don't know if that would be convenient instead of generating speech. This could be investigated.
Got it. Yeah. That sounds very exciting. Okay, so thanks again for your great talk and also being here, for taking your time. So I guess without other questions, we'll just move forward.